Okay, good afternoon, everyone. Thank you, Thomas, for the great introduction. So, I'll try to say it well. Y la luz fue. What you see in front of you is not the new kind of LED technology, like liquid LEDs. This is what we call bioluminescence. And this is not just harvesting natural organisms in the wild. What you see in front of you have been engineered by students. So yeah, you have two keywords here in this sentence. It's engineer and students. So the first one is about technology, and the other one is about the use, like how is it possible that only students get something so complicated and imaginative? Because nowadays this is possible. And this goes much farther than you can imagine. Biology is becoming a technology. This is just another example of genetic engineering. It looks very childish, all right? But the technology behind it is actually fairly complex. Those are bacteria that have been engineered so that when they receive light, they don't produce, when they receive light, they don't produce pigments. But when they don't receive light, this is a complicated logic, they actually do produce pigments. And the end is like reproducing the early age of photography. And the resolution of the photo is the highest possible because the size of the pixel is 1 micrometer, the size of the bacteria. What we are living right now is a very concrete technological revolution. We have now the ability to go very deep within the mechanics of life in order to create new programs. Programs that can make living things do things that are interesting for the human society. It's almost like Legos at the end because it's about taking one function from one organism that you think is useful and bringing it to another one and plugging it with another function from a different organisms. Actually, life is pretty modular because at the end, it's all about DNA. DNA is the universal language of the living. And all organisms speak the same language, so it means we can plug everything nature has invented so far. This is mind-blowing. Imagine using all nature has been invented for those last billions of years. This is crazy. And so far, when we think about biology, and especially bioindustry, we think about pharma industry. Big plants. Most of the drugs nowadays are actually made using microorganisms. But this is not stopping here, because one thing life is good at is not at only synthesizing molecules, is at creating polymers. And, big polymers, very big ones. And they're so good at it that we're actually made of those polymers. And it's not only about the plants, it's about the animals, and we actually know nowadays how to harvest those abilities. For example, you've probably seen this recently. Bolt Thread recently succeededly at creating a spider web, a synthetic one, not synthesized by spiders, but synthesized by yeast or bacteria, microorganisms. The thing is, that would be normally impossible, even if you would use spiders like spider farms. Spiders don't live with each other very well. So we had, if we wanted to use one of the most resistant material on the planet, we had to use a different way. And by bringing the knowledge, like the DNA program from spiders, to the bacteria, then those bacteria could produce efficiently those spider webs. And then they created these marvelous jackets. But how did we come to this? What's the real story behind all those revolutions? It really started about 60 years ago. 60 years ago, those two guys found out the real structure of DNA, the chemical structure. So that Watson and Crick, they got a Nobel Prize for that. And at that time, so before that time, we were more in a space of discovering, trying to figure out what is really the support of the living, what the support of information. But after this, after actually figuring out what's the real structure of the DNA, we entered a space of making, like the maker era, because then we could finally modify that structure. We could modify that information, something we couldn't do before very easily. And in the last 60 years, biology has lived and experienced a lot of different revolutions. And I'm going to just show one of them. It's been very fast. In the last 15 years, our ability to read code of DNA has exponentially increased. It got amazingly faster, amazingly easier, and amazingly cheaper. For the first human genome to be sequenced was about 15 years ago. It costed about $3 billion. You had about 300 or 500, hundreds of scientists that worked all together just to make one genome sequence. And it took 15 years. The program started in the 80s. But if you look at the price tag, it got down pretty easily and pretty fast. And this is an exponential grade. So if you look at 2001, 100 million, all right? But the most interesting part is between 2007 and 2009. In only 2 years, you lose 3 orders of magnitude. It's like the price decreased by more than 1,000 times. In only 2 years. This is unprecedented. You don't have precedent for that. And nowadays, the price is about $1,000. But with $1,000, it's not only something that can be done only by very big industries or very big laboratories. It's a price tag that is affordable to most of people, actually. So knowing about this, it's not anymore only a technological revolution, it's also a sociological revolution. We came from this to this. It's amazingly simpler, and you can put it in the hands of everybody. So what I'm going to present in the next slides, so it's again not about the technology itself, it's about how this technology became in the hands of a new class of people. Not only scientists, not only biologists, but also designers, architects, engineers. That's how the whole field started, actually. And reminds us, obviously, of the 70s, 80s, when the personal computers were invented, when the machines at that time were very complex, very big, very expensive. Very few people actually knew how a computer would work. And nobody would imagine what would be the future of society with computers. But then some people, because they will learn the know-how in universities, and because the price tag of components, electrical components, will decrease so much, then it will be possible for those people to come together, work in their garage, and invent their own vision of computers. And that was the break that enabled the whole revolution of personal computers we heard after that. And so this was Steve Wozniak's garage. Nowadays, we don't hack computers, not only computers, but we also hack biology. And biology is fairly complex matters, but because of synthetic biology, because of all those engineering tools, because it became also simpler and cheaper, then it means that a lot more people can actually get their hands on it and work together, not only in professional laboratories, but also in personal labs like this one, for example. And that's what I did, for example. And in this lab I created 5 years ago, we invented many kinds of biomaterials. We work, for example, on cheap electronical devices that will be biodegradable by using melanins. The melanin that you have normally in your skin, but here we extract it from yeast. And actually, this is a semiconductor, so you can use it to do thermal sensors. So it's a biodegradable thermal sensors. We also work on new kind of textiles using bacterial cellulose. We also work on pigments, and I will show you an example of how pigments can be produced by life just after that. So, and we did that obviously in the most weird place for a biotech lab, just to show you that professional labs don't have the exclusivity anymore of doing biology, and this is getting much more democratized. And this is one of the most important messages. It's not only about technology, it's really about the social use of biology, so la Paillasse. So let's get a step back. When we think about biology, and let's think about the life itself. How did it actually appear on Earth? Why is it here? Why does it actually get maintained? Why is it so sustainable? When you look at, let's make a small exercise. Let's imagine that we are all in a spaceship. This looks like a spaceship, right? So we are somewhere in space. And we are the last batch of humanity. There is nothing else, like everybody's dead, on Earth, and we are the last hope of humanity. We have to get very far to a new planet. And the thing is that this planet is actually very, very, very far. And we are only in this spaceship with a limited amount of matter and energy. The problem with closed space is you have to get very, very efficient at recycling everything. Otherwise, your wastes are going to kill you. And when you think about it, Earth is like a spaceship. It's a closed environment with a limited amount of matter and energy that is circulating the sun at dozens of thousands of kilometers per hour. And if we don't actually get attention, like how actually life got sustainable, we're going to just kill it. And it's a great lesson from the living, because at some point you realize that 3.5 billion of years is a very long time, and life actually succeeded to get from the 0 point to this point. And in a matter of only hundreds of years, we actually may destroy everything. So just looking at this image makes us reflect actually on the cycle of things. We have to get more renewable, and life is going to be the key for doing that. Just a few examples. This is a very famous one, is one of the most known pictures for biomaterials. How can you grow materials at home? What you see in the bowl are actually just water. It's just water with some teas and some sugar inside. And it would have normally stayed liquid if you would have normally done nothing. But because you added bacteria, a specific kind of bacteria that's going to eat on the sugar and the nutrients from the tea, then magic is going to happen. This is going to be transformed into cellulose. The cellulose that you see in the bowl is a thick matter. It's like foam. It can be dried, it can be cooked, it can be cut, you can do it. You can use it in many different ways. And it's been used, for example, to do jackets or clothes or objects. It's a very interesting materials. Another one is mushrooms. We all go to forests, and we always remark that sometimes on trees we have those very dense, very hard mushrooms. And some people harness actually that materials to make it grow the way they wanted. By doing this, they could create bricks that are useful, that are solid, that can be used to protect stuff, to protect objects for transportation, for example. But at the end, this is all biodegradable. If you put that in the soil for like 2-3 weeks, it's going to be degraded very fast, and all is going to go back to the life cycle. But if you keep it in normal air with normal humidity or moisture, it's going to be very durable. So it's an interesting application. And it's not going to touch only purely materials or inert materials. It's going to touch food, for example, fermented food. What you see here is a very mind-blowing application. This is cheese that was not made by milk. Actually, it's a vegetarian milk. How is that possible? Because when you think about it, milk is just biosynthesis by a cow or by a goat, for example. But if you take the same program from those cows and you put it in yeast, for example, or bacteria, at the end the process is the same. You're going to get the same molecule with the same mixture, and then you're going to get milk. So this is the milk, for example, that has been produced by the microorganisms. At the end, you just have to ferment it, and you get milk. And at the end, even vegetarian people can eat that milk. This is another example where it's not only about materials, it's not only about construction, it's not only about sustainability or way to interact with agriculture or animals. We are very bad at conserving things, and especially rare species like rhinoceros. What you see in front of you is a rhino horn that doesn't come from a rhinoceros. So the problem with rhino horns is people believe it's going to give them a lot of power, especially in Asia, and they buy up to 50,000 euros per kilogram of keratin from the rhino horn. Keratin is the same compound you have in your nails. It's the same one. So some people had the idea that maybe we could just take the genetic program to create rhino keratin and put it in microorganisms. We're going to synthesize this keratin. And at the end, we're going to get this powder that would normally, could be sold this way. But people will not believe, actually, this is real rhino horn. So what they did, and this is what you see on the picture, they made a paste out of this keratin, and they used a 3D printer to print a rhino horn. So at the end, you get the perfect mix between bioengineering and 3D printing to just copy what life has been doing so far and help the markets of rhino horn to destroy it, basically, because people are going to buy the same product at the end, and you won't need actually to get the original product from the rhino directly. So that's a great way of associating both worlds. Now about Pili. So Pili is a company I co-founded about a year ago, and started in the biohacker space I founded about 5 years ago, La Paillasse, I showed you just before. And the idea about Pili is about how do we get out of this era where 99% of all the dyes in the market are coming from petrochemistry. This is not sustainable, and we're not going to go back to plants or animals, because plants are not efficient at doing this, neither animals. Just to give you an idea, the market is so huge. If you would like, for example, to just take indigo. Indigo is what actually dyed that shirt or your jeans. You have a market need of 80,000 tons per year for indigo. The whole indigo is produced by petrochemistry. But if you will have to go back to plant production, as it was in the 19th century, for example, you will need a surface of plantation that is larger than Germany, just for indigo. So this is not doable at all. So there is another option, and again, the future for the industry are microorganisms. You can engineer microorganisms much faster. You can produce stuff using microorganisms much faster, much easily. You can engineer them so that they can eat waste. You can create an environment of production that has industrial standards, so it's much more easily controlled. That's the problem right now with plants or animals if you want to produce stuff naturally, because the reproducibility is very poor. So this is, again, a simple example that what life can bring to us. This is a technology that has not been invented by humans. We are just diverting it and making just associated or perfected for our applications. And this is what we can do with it. We use those dyes for inks, for some cosmetics. We dye fabrics with it, and you get the same efficiency than with normal natural dyes that you would normally find in carpets, for example, or from plants or animals, except that it's been produced in only a couple of weeks, for example, instead of months. We also explore interfaces between matters. This has been dyed by microorganisms that have grown directly on the fabric. So you can see patterns, for example, that are very specific to the microorganisms that has been used. So it's a very, very, very interesting interface between life and fashion. How do we wrap up everything so far? We are right now still living this digital revolution. Information has been available everywhere at a faster ever pace. But it's an information that is edited. It's not immediate. It's something that's still just information. It doesn't relate to the physical world. So right now, we have also the maker revolution that enables us at ever faster pace again to prototype things, to print, to invent objects that are useful to us in a way that is still, however, not very sustainable. Most things are still using plastics, using metals. How do we get over this? And that's where the biological revolution comes in. Biofabrication. Biofabrication is going to be the key so that the maker revolution gets its full wings, basically. Because that's the way everything we fabricate are going to be sustainable, and we'll be able to look at the future, and say that everything we do is going to be, for a better world. And what's interesting is, as I said before, it's not only about hard tech. You can do it in a soft tech. You can do it in a low tech. It can be applied by anybody, not only biotech engineers. It's now affordable even for designers or architects. This is coming actually democratized. So this is our new world. We're still pioneers, but this is a very helpful world we are looking into. Thank you very much.